Okay, hi everybody. We are officially getting this thing started. So I am going to be talking to you today about waves and exactly what those are and the different kinds and how it's going to affect things that we are going to learn a little further into the year. So bear with me as I have not done this very often. In fact, this is the first video that I'm doing. I don't know if it's the first one I'm having you watch, but here we go. So properties of waves. So what we're really studying right now is how matter, so the stuff that makes up everything, and energy interact when waves are generated, and then what the three main types of mechanical waves are, and then the different properties of waves. So basically, whenever we think of the word wave, I'm sure that something like this picture comes into your head. And we think of a wave in the lake or in the ocean. And it is pretty similar to what a wave actually is. So it's a disturbance, basically, that transfers energy from place to place. So just like this wave in this picture, there's energy that's being transferred by this water that can lift up a ship, and it's moving from one place to another. So remember here, when we talk about energy, the definition is the ability to do work. So the ability to move something is usually what we're talking about. So it transfers energy from place to place. And it might be different kinds of energy, and that's what we're going to talk about. So what can cause a wave? So we have to have a source of energy to be able to transfer it, right? And we're transferring it in some sort of medium. So that's going to be a word we're going to use a lot. It might be a solid, it might be a liquid, it might be a gas, thinking back to what you learned last year in science. It could make any of these things vibrate. So a vibration is a repeated back and forth or up and down motion. So it's making something vibrate. And when we see it vibrate, that's how we know energy is moving through it. So if we think about what the energy source is in each picture, let's think about the one with the water. What is the energy source here? It's going to be the hand, right? The human is causing the disturbance, putting energy from their body to the water, and it's spreading out, right? It's moving from place to place. Just like the person with the rope connected to the tree, they are creating the energy from their body, they're doing work, and they're moving that rope up and down, and you can see the vibration, the up and down motion, and transferring it from the person to the tree. And the tree is probably going to end up moving because of that. So a mechanical wave is really what we're talking about here. It can only travel through a medium, so it has to have matter, something to be able to travel through. So an ocean wave is a perfect example of this. It's traveling through a liquid. A sound wave is something we hear, just like you're hearing my voice right now, traveling through the air, which is a gas. And then we can also have a wave traveling along a rope, like that picture, which is a solid. So it can travel through all three types of matter. And those are called a medium. We also have something called an electromagnetic wave, which is something we will learn about. We'll learn about the specific types. So these don't have to have a medium. These are not mechanical waves. They can travel through empty space, like in outer space where there are no molecules of any type of air. So like X-rays, visible light, which is how we see colors, microwaves, radio waves that we can hear, and then ultraviolet, which we can't see, but some of you may have heard this. It gives us sunburn. Those are all electromagnetic, so they can travel through empty space. They can travel through air too, or liquids, sometimes even solids, especially in the case of X-rays, but they can also travel through empty space. So they're not mechanical waves. They are their own type. I'm going to skip that because we're not in class. So we have three types of mechanical waves. We're going back to the one that's just something that can travel through a medium. It can only travel through matter. So they're according to how they travel through a medium. So we have the first one, A, is a transverse wave. So that is going to be something we can actually see that goes up and down, just like that rope in the previous pictures. We've got something called a longitudinal wave, which is B, and that it looks kind of like a slinky. So that's going to be the example I'm going to keep talking about as a slinky for that one. It doesn't go up and down, it just kind of moves side to side. And then a surface wave is exactly what it sounds like. It's just like surface of the water. So transverse waves, the way to describe this is that the medium, so the medium would be the line that moves up and down just like a rope. That moves at a right angle to the way the wave is traveling. So the medium's going up and down, and the wave is actually transferring the energy to the side because it's going up and down to the right. So transverse actually means across. So if we think about a right angle, a 90-degree angle, like in math, that's what those two lines are making in orange. As it moves in one direction, so the actual wave is moving to the side, but the particles of the medium, that rope, would be moving up and down. So that's perpendicular. Here we go back to all that math that you thought you'd never use. Longitudinal waves are parallel to the direction the waves are traveling. So just like a slinky, that picture there, the medium is moving back and forth. And the energy is also moving back and forth. So we have two different parts to a longitudinal wave. We have a compression, as you can see on the far right, where the waves get really close together. And then we have a rarefaction, which is more towards the middle there, where they're spread out. So it doesn't have to be like a slinky with the rings. It could just be particles of something or molecules of something. And they move back and forth, side to side. And they can spread apart as a rarefaction or come together as a compression. And they don't have to stay a rarefaction or compression. They can kind of switch. They can move back and forth. There doesn't have to be a certain spot where you would just have one of them. So a surface wave is going to happen between two different mediums or media, like water and air, just like a wave. So the water is moving up and down like a transverse wave, as you can see on the top there. But it's also moving back and forth like a longitudinal wave. But water doesn't compress. So up and down, but also back and forth. And it makes the water particles move in circles. So that's actually what's happening in the water when you might be swimming, and it creates waves. And we're skipping this because we're not in class. So we have some vocab here with some of these things. A transverse wave here has a crest. So that top part where it is at the very highest point that that energy is going to make that medium reach. So that's the maximum height that that medium is going to reach. The trough is going to be the minimum height it's going to reach. So the very lowest point that it's going to reach. And then we have the rest position, which is that center gray line moving through. So that would be if the rope wasn't moving at all. That's what it would look like. It shows us how far the crest and trough is from that point. And then just like we talked about with the longitudinal wave, the compression is the crest, right? That's where the energy is the closest together, the most movement. And the trough would be the rarefaction, where it's farthest apart. So we also have something called amplitude, and you've probably heard of this before talking about sound. So amplitude is just measuring the distance between that crest and the resting position. So, or the trough and the resting position. So it's really how strong that wave is, how much energy it has to be able to move that medium. And it can also be measured in a longitudinal wave based on the measure of how compressed or rarefied it is. Wavelength is going to be the distance between two crests, might be, or the distance between two troughs on a transverse wave. So that's how long it takes for the wave to pass a certain point. Or on a longitudinal wave, it's the distance from one compression to the next. Frequency is going to be the number of complete wavelengths that pass a given point in a certain number of time. So we're not measuring how tall it gets. We're not measuring the distance between the two. We're just seeing how many vibrations happen per second. And we call that hertz. So 1 vibration per second equals 1 hertz. So however many times it passes in 1 second, whether it passes 4 times in 1 second, that would be 4 hertz. However many it is, that's the frequency. So speed, and we'll talk about this throughout the year, is going to be how far something travels in a certain amount of time. So we're kind of talking a little bit about frequency and speed together. So speed, wavelength, and frequency of a wave are related to each other, and there's actually mathematical formulas for it. You guys are going to be surprised. There is so much math in science. You did not get away from Mr. Osceola in this class. So the unit for speed is going to be meters per second, and we use meters because that is the system that science uses. The U.S. is the only country that uses the imperial system where we use miles and feet. But meters is the other system, which for some reason I can't think of the name right now, that the rest of the world uses. So we have all of these equations that we can use to figure out the frequency, the speed, and the wavelength, just by being able to switch them around on different sides of the equal sign. So do this problem, and we have the the formulas right there. A wave on a lake has a wavelength of 0.5 meters and a frequency of 2 hertz. So 2 hertz is going to be 2 waves pass in 1 second. To find the speed of the wave, use this formula. Speed equals wavelength times frequency. So we would take speed, because that's what we're looking for, equals wavelength, which they told us was 0.5 meters, times frequency, which is 2 hertz. So we take 0.5 meters times 2 per second, which is really what hertz is, right? And we multiply those together, and 0.5 times 2 is 1. So we get 1 meters per second is how fast that wave is moving. So that is a quick explanation of waves and the different types of waves. We're really describing how matter and energy are interacting, the 3 types of mechanical waves. Also, we talked a little bit about electromagnetic waves, which we'll get more into in another section, and the properties of waves, so all of that vocab. So this is just an intro for you guys, just to jump right in, be able to have some background information, and then we'll do some labs and some activities on this in class. So thank you for watching, guys, and I'm excited to see what you thought. I will see you tomorrow.